to our noontime seminar. To start off, acknowledge that the University of Colorado Boulder sits upon land within the territories of the Ute, Cheyenne, and Arapaho peoples. Further, I acknowledge that 48 tribal nations are historically tied to the lands that make up the state of Colorado. It is my pleasure to introduce Steve Montzka. He, not to steal his thunder, but he's going to give a talk that I think really nicely illustrates why and how science can matter, and how sometimes you can do good science and be able to point to something that you fixed in the world. So that's really exciting. Steve has had a very distinguished career as an atmospheric chemist at NOAA since the early 90s. He got his BS with summa cum laude from St. Lawrence University and PhD in 1988 from the University of Colorado Boulder. Works in the NOAA Global Monitoring Division and has won numerous awards, including being elected recently as a fellow of the American Geophysical Union. Won the NOAA Outstanding Scientific Paper of the Year award 9 times. It's like LeBron in the All-Star game. And relevant to today, he was nominated into the Montreal Protocol's Who's Who, and he's had many, many other awards and honors, and we're really delighted and honored to have him here.
Appreciate it.
Thank you.
Well, thanks for coming today. So I'm going to tell us a story, factual story, hopefully, that you can confirm with your own measurements of the atmosphere, if you like, involving the ozone layer, stratospheric ozone layer, and guiding ozone layer recovery with what I like to think of as effective science and policy working together on an international scale. And this is a picture of the Mauna Loa Observatory. My wife spent a lot of time there. In fact, I lost her to this region shortly after we got married for a brief time. But anyway, sunrise at Mauna Loa Observatory, where that plays an important role in this story. And I'm not the only person working on this. There's colleagues at both NOAA and CERES. And I'd like to thank a lot of co-authors on associated papers that we've been able to publish recently. And there's folks out in the field, station personnel, and at cooperative institutes around the world helping us with sampling those flasks, sending them to us, and also operating instruments located at the site. And there's another group an international group making measurements of halocarbons, ozone-depleting substances around the world that we have a very good interaction with. I wanted to also acknowledge. So just a little reminder, a background of where we're at. The ozone layer this is a figure of ozone concentration or partial pressure as a function of altitude. And so ozone abundance increasing. Down in the lower atmosphere, we have ozone, pretty low concentrations. And as we go up higher into the stratosphere, there's this big layer of ozone that filters out high energy UV radiation from the sun. These are graphics from the Q&As of the WMO ozone assessments, where real high energy UV doesn't make it through this layer. UVB, mid-range UV radiation, some of that makes it through to the Earth's surface. And enhanced UVB radiation from the sun raises the risk of skin cancer, cataracts, immune system suppression in humans, and then also many of the damages in plants, crops, and the natural system, aquatic ecosystem as well. And UVA is a less energetic UV radiation, mostly relates to skin aging, which I don't know anything about, so just a little wrinkly. Okay, so the issue with the ozone layer is that there's some depletion of it. It was first hypothesized in 1974 by 2 scientists, the University of California, Irvine, where they said that chlorofluoromethanes could be wafted up into the stratosphere and undergo and release their chlorine and atomize the destruction of ozone. So, 4,000 citations on a paper like this. You want to make sure you get the title edited correctly. That's a new word for me, that atoms. Okay, but what they found in this paper, what they hypothesized, was not expected to be a significant problem for many years. But then, guess what? Only a few years later, a paper was published by Joe Farman and colleagues that showed dramatic springtime ozone depletion. And this is ozone total column, so looking up towards the sun and being able to gauge the total density of column between you throughout the atmosphere. And they did this in Antarctica, and saw that and this doesn't go to zero, it goes to like 175 Dobson units up to 350 or so. But the concentration of ozone, total column, during spring, during October, was decreasing dramatically. Like the ozone layer was getting eaten away somehow. And I've seen some videos of that time, and you listen to the scientists talk, and they sound scared. They sound scared because here we have that shield. Have we done ourselves in as a human race to destroy that shield, that protective ozone shield, protecting us from high energy UV radiation? So, as a result of not much more than that information, there was agreed around the world. Countries got together and agreed to the 1987 Montreal Protocol on substances that deplete the ozone layer. And I don't know if it was in celebration of your birthday or
A couple months later, so
a couple months.
yeah, we got to ruminate on it a little bit.
Turns out he was born in Montreal in 1987. So yeah, all right. So the protocol was designed to heal the stratospheric ozone layer, limit UV exposure around the world at Earth's surface. It mandated a global phase out of production and trade of ozone depleting substances. And this was really before they actually had any smoking gun that suggested it actually was the chlorofluorocarbons. It was the first universally ratified treaty in UN history. In other words, all countries of the world have signed onto this treaty and many subsequent amendments. The parties have held 2 meetings per year. They're dedicated to seeing this problem through since that time. They've held 2 meetings a year to ensure its continued success, to understand whether or not they need to modify, adjust, revise the controls in the protocol to ensure that ozone depletion goes away, that we get recovery of the ozone layer. And what the protocol involved mostly, at least in terms of its effect on the ozone layer, was a stepwise phase out of ozone depleting gases, of the chemicals, CFCs in particular, used in refrigeration, air conditioning, foam blowing, solvents, fire extinguisher, even as a pesticide. To substitute these with a first generation of substitutes, the hydrochlorofluorocarbons, they also contain chlorine, but they were less efficient at destroying ozone. And industry said, if you really want to get rid of these quick, we can substitute it with these, the HCFCs. And so they agreed to that. And then the second generation are the hydrofluorocarbons. No chlorine, no bromine, no ozone, direct chemical interaction with ozone, stratospheric layer. And full implementation is expected to yield avoidance of millions of cases of skin cancer and millions of cases of cataracts in the US alone, with even greater benefits worldwide. So, Kofi Annan describes the Montreal Protocol in 2003 as perhaps the single most successful international agreement to date. Adherence to the protocol has led to near elimination of ozone-depleting substance production, particularly chlorofluorocarbons. This production of ozone-depleting substances, or ODSs, and CFCs, which make up most of the ozone-depleting substance production, gets reported to the Ozone Secretariat each year. And this is a record of that reporting by all the countries of the world. You can see the CFC production was mandated to be phased out in 2010. It was actually near zero before that, slightly a few years early. So, case closed, right? We're done. We can just walk away and ensure that in a few years' time, maybe next year, I don't know, the ozone layer will be healed. Well, despite a warning over 45 years ago, this paper that I mentioned, and the universal ratification of the protocol, even today, the stratospheric ozone layer is far from recovered. This is a picture of that ozone layer over South Pole. This was October of 2018. The red line is that same picture I showed you before, where here the ozone layer was a nice big layer, higher concentrations as a function of altitude, pre-ozone hole. And from 1991 to 2012, the average ozone layer that was observed during October shows this big hole eaten out of that ozone in this altitude range. And even in 2018, there was a big bite still out of this ozone layer, suggesting that ozone depletion is still substantial. Are we making any progress? Why is this happening? Well, in fact, we are. The good news is that there are signs of initial recovery in the mid-latitude stratosphere, where the depletion is much smaller compared to what happens over Antarctica during the springtime. So what do I do? And why am I here today? Well, I make measurements of ozone-depleting gas concentrations around the world at a number of different sites using different techniques. We get weekly samples in flasks filled at these different sites that are indicated in white, and we have some instruments located on site to measure subsets of those gases at these sites indicated with red symbols. And the main purpose of that, well, okay, so from that, we get air samples sent to us or have measurements being made on site. We measure 40 different gases or so that include Montreal Protocol controlled substances, those gases that are responsible for depleting the ozone layer. And so the main purpose of this project, the reason why it was initiated years ago, was to provide an independent assessment of the Montreal Protocol itself. Is it working? We have folks agreeing to phase out the chemicals. They report that they have. Did they actually? Has it had the impact that we expected? Because really, whether or not ozone depletion continues depends on what's in the atmosphere, and that's what we measure on a day-to-day basis. Now, so this means really that I'm a glorified accountant. I make measurements, I look at numbers, it's going up, it's going down, great. Well, I've been doing this for nearly 30 years, and there's no way I could have been nothing against accounting, but there's no way I would be able to do that and stay engaged for so long. And in fact, this resource that we have of these air samples coming to us allow us to take the chemical pulse of the atmosphere on a weekly, monthly, seasonal, yearly, decadal time scale. That's a unique resource that actually we can address all sorts of interesting scientific questions related to how the atmosphere works, and that's what keeps me engaged day in and day out. In addition to this right here, and communicating things like this, in particular, to a wider audience, in particular policymakers. So, from our measurements of these gases around the world, the CFCs, HCFCs, chlorinated solvents, the bad chemicals that are depleting the ozone layer, we can see that adherence to the Montreal Protocol has led to the declines in the emissions and concentrations of these ozone-depleting substances. So I have here from 1990 to nearly the present day, the ozone-depleting chlorine contained in all these chemicals and the ozone-depleting bromine contained in all these chemicals. Now the scale doesn't go to zero on these, but these are like 10 to 20% declines since the protocol came into force in the late 80s, early 1990s. So you can see that the protocol has made a difference in the concentrations of these gases allowed because the production was phased out, reportedly. We now have an atmospheric response that occurs with some time lag. And the concentrations of these gases, the threat to the ozone layer is decreasing. Now, when will the ozone hole go away? Well, it's projected that the concentrations of chlorine and bromine in these gases that have been controlled should decline to pre-ozone hole levels later in the century, like somewhere between 2050 and 2080, depending on where you want to talk about in the stratosphere. So not for quite some time. But there's one important caveat to that, and that's provided continued adherence to the protocol's controls on these substances. And we regularly update progress on these concentrations and this decline at that particular website in case you're interested. Now, why do we anticipate it's going to take so long, decades? And the main reason is the recovery time is set by how rapidly these chemicals get removed from the atmosphere. And that's set by natural processes, the removal rates of CFCs and other gases from the atmosphere, either by photolysis in the stratosphere or by removal oxidation in the lower atmosphere. When these chemicals either get photolyzed or react, then they get scrubbed from the atmosphere, they get solubilized into aerosols and other things like that. CFC-11, for example, has a 50-year lifetime. 50 years. 1 over 50 years is 2% per year. So 2% of the atmospheric burden of CFC-11 gets destroyed by natural processes each year. That's not very much. And it's going to take a long time for its concentration to continue to go down. CFC-12 present in even higher abundance than CFC-11 has a 100-year lifetime. 1% of that gets removed from the atmosphere each year. The substitute chemicals, hydrochlorofluorocarbon, has a shorter lifetime. So about 9% of that gets destroyed. And this chemical 134A that you have in all your car air conditioners, until maybe recently, it's been substituted with another one, has a lifetime of 14 years. So on the order of 7% per year of that chemical gets removed from the atmosphere. So what do we see? We make measurements at all these different locations around the world. We average the results by hemisphere. That's what I've shown here. Results for the northern hemisphere over time over the past 20 years. in red, and in blue, the average in the southern hemisphere. And this is at Earth's surface. And we can see declines in the main ozone-depleting substance, CFC11, and declines in methylchloroform. And note, too, that I've plotted the concentration of methylchloroform here on a log scale. And if you're familiar with kinetics, you know that this means first-order exponential decay of methylchloroform for 20 years. It means that the role of emissions were probably fairly minor on this system. It gives us insights into the loss processes of this chemical, which happen to be an important loss process for many chemicals in the atmosphere. One of the reasons I keep staying interested and excited in the science that we can do. One of the first generation substitute, HCFC, starting to tail off a little bit, not increasing as rapidly anymore. And that's because the production was capped, frozen at 2013, and now is gradually being phased out and will be phased out over the next 10 to 15 years. And this is one of the HFCs, doesn't deplete ozone, but is a greenhouse gas. They're all greenhouse gases, actually. Concentrations still increase fairly significantly and unabatedly. Let's look a little more closely at CFC11. If you were paying close attention, if you had your eyes geared on these changes over time, you see something a little different happening in the most recent years. Does it matter? Well, it does. CFC11 is the second most abundant ozone-depleting substance in the atmosphere. It still accounts for a fifth to a quarter of the ozone-depleting chlorine being delivered to the stratosphere. And this decline actually right here through this period anyway was also significant, a main reason why that total chlorine picture showed a decrease over time. It was the largest contributor to that decline. And note too that while production was reportedly phased out in 2010, significant emissions persist. And that's because this chemical was used in large part to make foams. In particular, in building insulation, refrigerator insulation, things like that. And those are closed cell foams. So it turns out that you make a foam, the way it happens is you get a fluid in there that turns to gas and you make tiny little bubbles. That's where the CFC11 resides. And so there's this huge bank of CFC11 existing in foams around the world today. And as that bank as the CFC11 slowly escapes from those foams, that sustains the emissions in the atmosphere of CFC11, and will for quite some time. So it's not only the removal rate of the chemical from the atmosphere, but it's also a sustained emission from this reservoir. Emissions of F11 aren't zero. But if you look at this carefully, you see that, my goodness, it looks like after production was reportedly phased out, the chemical concentration decreases more slowly. And that's exactly opposite of what we'd expect. You've got this bank of foam, CFC11 contained in a foam, and one year, a certain amount of it gets emitted, and the bank is smaller the next year. So the amount that gets emitted from that bank should be smaller. The emissions should decrease over time, and the concentration decline should accelerate. Instead, it slowed down. This was a shocker. How on earth could this be happening? We expected just a little bit more. We expected it to decrease more rapidly. This is the global growth rate. It's declining in this period of time at 0.8% per year. And what rate did I say it should be in the absence of emission? 2% per year. Right. So it should be declining like this if emissions were zero. We know emissions shouldn't. We don't expect them to be zero because of this reservoir, but still, we're much above that. And then the decline slows down. It slows down by a half, approximately. And at the same time, as concentration slows down, you see an increase in the concentration difference. And this is important because emissions of anthropogenically used gases are primarily in the northern hemisphere. So when the emissions increase, the north to south difference also increases in concentration. And so that's a good indication that maybe our first pass guess at what's going on here was an emission increase for CFC11 after production was reportedly phased out. So I saw this, I couldn't believe it. Given the time, effort, blood, sweat, tears, money throughout the world, parties of all countries of the world have spent on trying to solve this problem. We see this, or is my instrument just broken? That's something that as analytical chemists you got to be aware of and be careful about. We don't want to go announcing to the world that, oh, a screw fell off my instrument, and that's why I'm not getting the right results anymore. Well, it turns out, no, I don't think so. The slowdown was observed by independent measurements. We measure CFC11 3 different ways at NOAA. There's another group I mentioned before. They also make measurements of CFC11, also seeing this independently. We use multiple techniques, and the different aspects of the data show this anomaly, both in the distribution and in the change in rate. And if there were an error in the measurements, it's not likely that it would be reflected in both of those things. Is it unique to certain sites? Is there just one site that's causing the problem? The answer to that is no also. Well, here we have monthly means from 12 different sites around the world going down over time. Those 8 sites in the northern hemisphere are all slowing down the concentration at each one of those sites. And in fact, they overlay each other very nicely. Southern hemisphere, there's a little bit more variability, given that that's a zone of gradient between the north and the south. The Samoa site is at 14 degrees south, so it sometimes sees more northern hemisphere than not. But it's not happening only at one site. It's happening throughout the world, a little bit delayed in the southern versus the northern hemisphere. So we use these measurements to derive emissions, global emission rates of different chemicals. And the way we do that conceptually is to say, I make measurements, I think I can estimate the global atmospheric burden of this chemical from one year to the next. And we know that the loss rate should be, in the absence of emissions, 2% per year. So if we consider that what we measure in the atmosphere reflects the balance of how much comes in, emissions, and how much gets removed, and we think we know what that removal rate is, we can say the concentration record is here. It should have gone down in a year by 2%, but in fact it didn't. And so this balance here is the emission rate. And so we can gauge for each calendar year how much emission was required to sustain what we actually measured in the atmosphere. And so that simple mass balance consideration, rate of change equals emission minus loss. And you derive emission history for CFC11 in the atmosphere. And I've shown that here, that's what the black points are, relative to the reported production in green. And you can see that emissions and production were coming down nicely together up through early 2000, and then production kept going down, and emissions no longer continued to decline. First question mark. And then it goes up, which doesn't make any sense. Up by 25% or 13 gigagrams, that's a lot of material. And this plot goes through, you know what, I don't have these lines in the right spot. This is 2014, this is 2015, this is 2016. So I messed up that scale somehow, sorry about that. 2017 and also 18 are similarly elevated in their emission. And as I said before, is it really that the emissions are increasing, given all the time and effort that's been spent on this? And one important little wrinkle in this is that we've assumed that loss per year to that 2%. You can see it was a big term in the budget there. We've assumed that it's constant from one year to the next. And there's a chance that varies due to different processes, the way the atmosphere works. If you know about the quasi-biennial stratospheric oscillation and winds and other things like that, they can affect that term, but typically it affects it on an oscillation, not on a one time period versus another averaged time period. So we spent a lot of time looking at this to be sure that when we announced to the world that emissions of CFC11 were increasing, that it wasn't due to a change in how the atmosphere was actually working. When we did this, we used 3D models and their ability to understand how atmospheric transport changes over time and things. And they suggested, actually maybe some of this increase, maybe about half of this increase might be due to changes in how the atmosphere works. My modelers that I have helping me out have since revised their tune, but that was after we published the paper. But we'll fix that in the next paper. But at this point in time, I was like, are you kidding me? Really? The model suggests the atmospheric processes may have changed by some amount. We don't know exactly how much, but some degree that might mean the emissions didn't increase by this amount. Did they, the next question is, well, did they increase at all? Really? And so what I did as an observationalist, I looked very carefully at the measurements to understand were there any hints in the observations themselves that actually suggest an emission increase. And it turns out that air reaching Hawaii in autumn can be influenced. It's downwind of Eurasian emissions. And so I looked carefully at the results from the Mauna Loa station, that picture that I showed in the original slide for the presentation, right smack in the middle of the Pacific, downwind, receiving influences from Eastern Asia. And what I noticed is that before 2012, pollution plumes that reach our site in Hawaii didn't contain elevated levels of CFC-11. But after 2012, the pollution plumes reaching Hawaii contained elevated CFC-11. Not much, but some. Really pointing to the fact something changed upwind of this region. Well, and here's a brief example of the data that went into that conclusion. Here is HCFC-22, used in those square window air conditioners, at least until a few years ago, throughout the world, in particular in Eastern Asia. You see the concentrations varying. This is the concentration, higher concentrations up higher, and as a function of fraction of years. So 0.5 is what, from beginning of June or beginning of July through to the end of December. 2010, 2016. And we see variability. This is a 5% change. Each point is a sample, a weekly flask sample, the collection of 2 flasks in parallel. And the mean and the standard deviation of that result is shown here. We can see we can measure it pretty well. And we can see this variability in the atmosphere. And we see covariations in other gases that are anthropogenically emitted gases, a solvent called dichloromethane and carbon monoxide. So we see this variability equally throughout this period. I've shown these 2 years. How about F11? Well, F11 during 2010 is moving to its own tune, moving to its own dance. It's not correlated with the pollution plumes that are coming with enhanced levels of HCFC-22. In fact, the regression coefficient or the correlation observed for those gases is insignificantly small during those years. How about 2016? Things have changed. When we get a pollution plume coming through, now we see this enhanced concentration of CFC-11. In fact, the correlation coefficients are now very significant. Really pinning down the point that this looks to be enhanced emissions upwind of the Mauna Loa site. Do we know where it's coming from actually? Well, there's meteorological models of wind, direction, and speed, and we can look at those models to understand at any point in time that we could take a sample, where was the air in the few days or weeks beforehand? Where does it come from? What surface regions are influencing the concentration of the gases that we measure? And those surface regions, when we would measure lower concentrations of these pollutants during this period of 2013 to 16, when we measure lower concentrations, we see surface sensitivity due to the background oceanic marine boundary layer. No surprise that there aren't any anthropogenic enhancements of anthropogenically emitted gases during when samples contain this impact. We do have some influence from North America, however. How about the higher concentrations? Higher concentrations of these gases, and look what region of the world lights up. Those samples were associated with air that clearly at some point in time was influenced by this region in Eastern Asia. And so this was kind of, for us, allowed the conclusion that some portion, we weren't able to quantify it, the global emission increase was from Eastern Asia. Now, I've got colleagues in the A-gauge community. They actually make measurements in this region of the world. And they, with some urging, it didn't take much urging, started looking carefully at those measurements made in that region. And lo and behold, they saw this, CFC-11 concentration from 2008 to 2018 at the Ozone and Hataruma stations. And if you look carefully at this record, you see the evidence for pollution plumes coming to this site. And what we have is the colored zones, the colored lines are measurements at these 2 stations. The gray that you can pick out here is what you see at Cape Grim, Tasmania, in the southern hemisphere. Not much variability at all, nice background concentration. And in the northern hemisphere with no emissions, you imagine that that would only be slightly higher. Clearly evidence for emissions upwind of this site. And if you look carefully too, that the enhancements on average get bigger. And they get bigger about here. I I've just drawn some lines in. I could have done it quantitatively too, looking at the distribution of the enhancements above back concentrations, other things like that. Yes?
Just a quick question, but overall the trend looks like it's going down?
Yeah.
But you're saying the plumes are increasing in size, but what
Yeah.
about the going down part overall?
You missed the first figure.
I'm sorry, I was like, yeah.
Concentration of CFC11 is decreasing in the atmosphere.
Okay, sorry.
So the balance of sources is not outweighed by the balance of removals.
Okay.
So on average, it's going down in the
But it's
atmosphere.
these spikes that are doing.
Yeah, these spikes are telling us something upwind of this region
Gotcha.
has changed over time, has increased. And these folks did what's called an inverse Lagrangian model analysis of these measurements, of those pollution plumes. If you know accurately enough where the wind came from and the speed that it took to get to your location when you made a measurement, you can look at those pollution plumes and infer emission rates for the regions upwind that air sample was sensitive to. And they did that, and they inferred that the difference between after 2013 and before 2013, these regions of China show up. Two provinces, Shandong and the Hebei provinces, show up as being the regions of this sensitivity analysis that clearly showed emission increases for CFC11 during this time period. Now the thing is that only about 50% of the global emission increase comes from these regions. So some comes from somewhere else. Where's the other half? Question you asked. And the answer is, we don't know. You know, we make measurements, similar observations. I showed you a network of the places where we make measurements. We also have quite an extensive, about two dozen different sites from aircraft, from towers over the US to show, and if we looked at that results, to show that emissions of F11 over the US are fairly small, less than 10 gigagrams per year. The increase was 10, but the total emissions for the US is less than 10, and no recent increases. And the same analysis has been done for Europe, also for Australia. But I didn't mention Russia, India, Indonesia, Africa, the Middle East, South America. Regional estimates from many parts of the world aren't possible because we're not making measurements in those regions of the world. So we're blind. We happen to be lucky in this instance where we could capture, using these measurements in Eastern Asia, at least some of the activities that were responsible for what we observed in the global atmospheric background, that global atmospheric emission increase. So, one important thing about the protocol, especially with regard to policy and regulation, is that emissions aren't controlled in the Montreal Protocol. It's only production. And yet, what do I measure? I measure concentrations, and from which I infer emissions. I don't know anything about production. Right. So the question is, do the results really imply a violation of the protocol? Can we really say, or not, that emissions, or that production actually changed, particularly given that there's this huge reservoir of CFC11 in this foam bank? And foam bank that might be 1,200 or 20 times the annual emission rate. And what we did is we looked at this emission record. We think we know what the bank is, and you can do a mass balance for the bank. You think you know what reported production is, so additions to the bank. You think you know what the bank size at a particular year is, and we have emissions, losses from the bank, and we can calculate that emission fraction from the bank each year. How much of this bank is getting released to the atmosphere each year? And it turns out that it was on the order of 5%, maybe decreased to about 3.5%. But if this record of production is correct, then this release rate, this escape rate for this foam reservoir, foam in buildings, foam in landfills, foam in old refrigerators, would have had to double over about a decade. And I'm not the expert on this, but there are many experts in industry who monitor these kind of things over time, say there just isn't any evidence that the releases or the destruction of this foam bank was accelerated after this period of time, therefore pointing to likely this emission increase being the result of a violation of the protocol. Somebody producing CFC11 after it reportedly was phased out. So what does it mean for the ozone layer? Well, it turns out that even though multiple years went by where we were checking our P's and Q's and measurements, ensuring that We weren't going to give the wrong answer. Make sure that our conclusions accurately reflected what we measured in the atmosphere. If the problem's rapidly fixed, the impact of the ozone layer should be small. But if emissions continue, ozone recovery delay could be substantially longer. 7 years, 20 years, depends on where you look and what that emission rate is. Now, you consider, given that maybe some of you have heard of this issue in the news because it was in the news a lot, there's been a lot of attention about it, that seems pretty unlikely. And I would say, yeah, perhaps, but know that the magnitude of the problem really ultimately depends on how much was produced. You know, if it was used for phones, and folks think that that was the most likely use, if it was used for phones, then most of what was produced actually still in those phones. And what we detected in the atmosphere might only be the tip of the iceberg. Just what was released inadvertently in the process of making and using these phones. And if so, then if we've augmented this bank, this reservoir of CFC11 substantially, then that means we've locked in enhanced emissions of F11 for some time in the future. So I didn't talk too much about this, but I showed an emission increase. It's about 13 gigagrams per year before and after 2012. Actually, but we expected the emissions to go down over that period, so that unexpected emission rate actually is significantly higher, maybe 20 to 30 gigagrams a year. Folks tell me that that could imply 50 to 100 gigagrams of CFC11 production. And the peak production was only 4 to 8 times larger than that. So a substantial amount of production, potentially. And augmenting that bank as well. Okay, so global reaction to the results. You know, it was amazing. Both the New York Times and this non-governmental organization, Environmental Investigation Agency, went on the ground, undercover, into China, looking for evidence of CFC11 use. And they found it. But the issue with that has always been, they surveyed a few folks, they got some positive answers that yes, there's CFC11 being used. And the folks say, oh yeah, you want CFC11? I can give you CFC11. You know, it's hard to know. The issue was the overall quantities were never well known. But now we know from the atmosphere integrates all those processes, that it was significant. It was very interesting that these folks went on site and saw that. The parties to the Montreal Protocol, those folks that I mentioned, meet twice a year to ensure that the protocol ultimately is successful. They've taken this issue very seriously. In fact, the Ecuadorian president, Mr. Lenin Moreno, opened the meeting in Ecuador recently. And this is the science assessment panel, the folks from the scientific community who provide scientific input, more clarity on the issues that are coming up. And they even let me tag along during this meeting and give presentations to the parties at side events to answer their questions, provide them more information so they're in a better position to make intelligent decisions about what to do. So what is being done? Well, the parties to the protocol, as I mentioned, are taking the issue seriously, but they're looking for more information. They want to facilitate rapid mitigation. They also want to maintain the integrity of the protocol. Some country says, I see China emitting tons of CFC11. My footprint is minuscule compared to that. Why do I care about continuing the pain and suffering of abiding by the Montreal Protocol? There's a potential that the protocol unravels. I don't think that's going to happen. These folks are dedicated. They're looking for more information. They're trying to answer a number of different questions, like ozone layer impact. Are there regions outside of China where emissions are increased? What led to the issue? Why did this happen? How was the CFC11 produced in light of the fact that there is some monitoring agencies around the world? You know, how was it produced in a way that got missed? They're also considering a number of different things. They have some leverage on different countries, different parties to the protocol that is written into the protocol. They're reconsidering money being transferred to China. China is a developing country, categorized such in the Montreal Protocol, based on how much they used in the late 1980s of the ozone-depleting substances. And there's this multilateral fund that facilitates a transfer of technology and money from developed countries to developing countries. And China, for example, has gotten over $1 billion since the 1980s to facilitate their phase-out of these different ozone-depleting substances. And China's most recent funding allotments were dramatically reduced. Not specifically outlined with respect to this issue, but potentially that's the case. They're also considering punitive action, maybe remedial action too, the parties are. They're also considering revising the protocol in order to prevent future violations because they see and have seen some weaknesses in the structure of the protocol given this issue that they would want to ensure don't happen again, in particular because we're now in the process of phasing out the first generation substitute chemicals, the HCFCs, and the HFCs are being phased down by the most recent addition to the protocol, the Kigali Amendment, that addressed HFCs, even though they're not ozone-depleting substances. And that's because the protocol wants to retain the climate benefit that they provided in phasing out these greenhouse gases that are also ozone-depleting substances. So China's response, China has repeatedly indicated and throughout time has indicated a commitment and a dedication to this process and healing the ozone layer. And they've committed to work with country scientists and experts to locate and eliminate the true source of the increased emissions. They conducted numerous inspections throughout their country after we published our paper and found instances of illegal production and use, but like those other New York Times and Environmental Investigation Agency reports, the amounts that they showed and talked about were just nowhere near enough to account for what we were seeing in the atmosphere. So there's some gap there. But despite that, and actually despite being fingered, this was before that second paper came out that actually fingered China. Before that, they were formulated a plan of action with international input to develop a number of different things. First off, for me, most importantly, a national scale atmospheric monitoring system of ozone-depleting substances and their substitute chemicals. They are going to know, hopefully, if they make the measurements well enough, they're going to know for themselves whether or not they have a problem with compliance within their own country. They build test laboratories. So you get a new foam, you want to know if it's got some banned substance in it, you can put it to the test laboratory. They're strengthening inspections and enforcement. They're tracking better, they say, the source material used to produce CFCs, and a number of other things where they're trying to make a difference. So, I've made measurements, continued in the fortunate position to be able to continue to make measurements, and they hint at changes in all three respects that I've talked about before, and that is the global rate of change, the north-south difference, and then the concentration of pollution plumes of F11 as they reach Hawaii. They've all changed in a way. Here's the atmospheric record all the way to the end of last year. And right at the end there, you see that maybe, just maybe, is starting to turn over a little bit. And the north to south difference is a little bit reduced compared to what it was during the years. Maybe more like these years. So maybe, in fact, emissions of F11 now, again, are on the decline. Wouldn't that be nice? A nice success story. And you can be sure that every day I'm looking at the instrument results, putting more points on the plot to understand how this is changing. So this is a policy community. I thought I would just spend one slide to say a few things about the Montreal Protocol that I think enable its success. And one is it has repeatedly been revisited, adjusted, and amended by the parties with input from 3 expert panels: scientists, technology and economics experts, and folks related to environmental impacts, skin cancer folks, things like that. And as a result, this protocol has been revised a number of times. So without any protocol, this is reactive ozone-depleting halogen concentrations over time. 2000, here we are present day, 2020, and into the future. Without a protocol, these concentrations would continue to increase unabated in the atmosphere, caused huge amounts of ozone depletion, a huge problem for humanity and the biosphere. The first Montreal Protocol wouldn't have done much at all to change that. Initial agreements would have not saved the ozone layer. And so we think about other protocols related to climate, maybe. To have a protocol first time solve all the problems is maybe asking too much. I don't know. But it's only with subsequent revisions where the issue was revisited, and the scientists kept telling the policymakers, this is a problem, this is a problem, this is a problem, and it's getting worse, that the different subsequent amendments allowed for and projected, and now we observe that the concentrations of these ozone-depleting substances are decreasing and will decrease and will allow the ozone layer to recover. believe it or not, the decisions in plenary are typically made by unanimous consent. Everyone has to agree in order for decisions to move forward. This is all countries of the world. All 197 of them. It's rather amazing. They do a lot of backdoor finagling. You can count on that. And discussions that I'm not privy to, just sitting there listening. But boy, to see one day, HFCs are not ozone-depleting gases, and the next day, have them agreeing to controls, is kind of an amazing thing. A 10-year grace period was allowed for developing countries to abide by these phase-out schedules. And also, compliance by the developing countries is assisted by that fund, that transfer of money and technology that I mentioned earlier. I think that's an important part of this process too. So concluding remarks, I think the Montreal Protocol represents a unique situation in which scientists and policymakers are working constructively to enable ozone layer recovery in a back and forth, regularly updated kind of interaction. That information feedback loop, mostly through every 4-year reports, has led to the strengthening of controls and thereby improving chances for success, as I showed there. Scientists have input to the parties without interference. You know, it's a matter of we do our science providing policy relevant but policy neutral information to this community, and they receive it, and they receive it in good faith, as far as I can tell. Leverage on compliance by parties is enabled by multiple mechanisms. So there is some teeth to these decisions when things go awry. And for me, you know, state-of-the-art atmospheric monitoring, going to a number of places repeatedly, making regular measurements, trying to do it as best you can with the highest quality that you can, allowed us in this instance early detection of a significant violation of the protocol and an indication of the location even of this renewed source. And many questions remain for CFC 11, but the early signs suggest that the path to rapid lasting mitigation remains unclear, given that this bank could have been substantially increased. And we consider the future and our atmospheric vigilance capability. Is it up to the task? And especially when you want to consider these other chemical classes, but ultimately and hopefully greenhouse gases. So I think that's it. This is one of the meetings in November in Rome, where up at the dais there, addressing the parties, which was good fun. Happy to take any questions.
So, is a story well told? Thanks very much.
Of course.
Early in your story, you were talking about bromine,
Yeah.
and then it kind of fell away.
Yeah.
Is that because, or maybe I just put it in the form of a question, is it relatively negligible? I know that the way in which you talked about the sources in China is not a question of bromine, but in terms of just contributions to these challenges, what role does bromine play?
Bromine plays a significant role because it, on a per atom basis, is maybe 60 times more effective than chlorine at destroying ozone. That catalytic cycle that destroys ozone in the stratosphere is much more efficient for bromine. Mm-hmm. So it's not, chlorine is the dominant player, but bromine is also significant. The main bromine-containing gases are halons, which are fire extinguishing agents, and methyl bromide. And methyl bromide was extremely contentious for many years for a number of reasons. One being the fact that it has a large natural source, in particular from the oceans, also for biomass burning, things like that. And so there was some contention for a long time whether or not, if we no longer can sell strawberries because they are fumigated with methyl bromide, and that's why we have them in our grocery stores. If you're going to tell me I can't sell strawberries anymore to the world, we better get some kind of benefit out of that. And you can't guarantee me, without knowing very well that budget of methyl bromide, that some benefit will result. Ultimately, the science was able to determine the relative fraction of anthropogenic and natural emissions, and that's borne out to be reasonably accurate over time. And it was about 30% anthropogenic, 70% natural. And we've been able to watch the methyl bromide concentration come back down, close to, but not yet at, the background levels that we derive from firn air measurements, and ice core measurements. The halons are also a bit contentious because you're flying in a plane and a fire starts. And it is halon that makes sure that that fire goes out, doesn't take the plane down, but doesn't asphyxiate you. It's no good to land, or it's no good if everybody gets, the fire gets out and everyone in the plane's asphyxiated. So, and there's not really substitutes for those halons still. They have equally long lifetimes, but there's been a process of really making an effort to recycle those halons so that we don't produce more. In fact, the thought is that we may have to turn to producing some to allow for these critical uses for which substitutes haven't yet been proven in these critical applications. So bromine, somewhat less of a contribution, but still important and part of this process, sure.
Is that part of your monitoring as well, just not
Yes.
part of the story you told?
Yeah.
You're also monitoring
Yeah,
it?
that plot that I showed in the beginning was chlorine changes on one hand and
Yeah.
bromine changes on the other, and that bromine was methylbromide in the halon. So we are monitoring what we think to be the most prominent and important brominated gases. And there's a whole suite of naturally produced gases that are shorter lived. And there is a question of whether or not those chemicals actually contribute to the background level of bromine in the stratosphere. And with chlorine being enhanced, does that add to an more efficient ozone destruction pathway? Potentially. But so we monitor those naturally produced brominated gases too. We haven't seen large changes over time that perhaps could happen given climate change. But those kind of big changes have not been detected yet. So a big part of what we're looking at is anthropogenic activities, how they change over time, but also the natural system and how it changes over time. Not only loss rates, but also emissions of these other chemicals that can play a role.
How much time went by before you first started to notice a problem before, like, pinpoint, oh, it's coming from this area near China?
Yeah. I went in front of the parties to the Montreal Protocol shortly after I announced this finding in 2018. And the only grief I got was that, why didn't you tell us sooner? You know, what took you so long? And, you know, we were looking and seeing this anomalous slowdown. Well, first we noticed that it had decreased only linearly, where we expected to decrease this concentration to decrease more rapidly over time. That was the first clue that something unusual was going on. But this most recent increase, we knew around in 2015 that something unusual was happening. And so I spent a lot of time trying to understand, first, whether the measurements were good. Second, trying to understand whether the atmospheric processes, that lifetime of F11, was playing a role so that I can understand whether or not it truly was an emission change. So paper was published. As soon as I found that additional information from Mauna Loa that allowed me to say, you know, some part may be dynamics, but here's pretty darn solid proof that some part is emissions. As soon as we had that, the paper was published within a year. So 2015, noticing thing, the paper came out in May of 2018. And then the subsequent year, May of 2019, was when the second paper came with the measurements downwind of China. It pinpointed that country. Yeah.
So how confident are you about the 2% decay rate in the CST11?
Yeah.
How was that established? These chemicals have been around a long time.
Yeah, but you can guarantee that people have studied them quite extensively. You know, we think the scientific assessment of that lifetime and that loss rate comes from laboratory studies, and then incorporating the photolytic cross section. That is, you know, the number of molecules that get destroyed per flux of light in as a function of wavelength. Those have been done in detail, and that kind of information then is incorporated into a model to derive those loss rates. And you're right, we don't know it exactly, but if we shifted that emission history up or down because the lifetime was 50 or 55 or 60 years, it really wouldn't change the story. The biggest issue is whether or not that lifetime changes from year to year. And if there's anything interesting, well, the science that I anticipate coming out of this will be us enabling the science to understand how that lifetime changes from year to year in a better way. So on a year-to-year timescale, when I look at these results, I can see bumps and wiggles in that emission history. Some of them aren't from emissions. Some of them are from a regular variability in the way the atmosphere is working. And I think, especially when we come down to, now, Steve, tell me, what happened in 2019? Can I give you a 1-year best estimate of emission, given that these dynamical processes may play a role? I think our science is advancing in a nice way that ultimately, yes, I will be able to do that. I hope to be able to do that within 6 months, actually. So,
Has China pushed to put more sensors in other countries to find the rest of it?
not that I've heard. Yeah, know that the region that this site in Gosan and the sites in Gosan and Haruma, they were really only sensitive to that region that was not crosshatched. So it wasn't all of China.
Right.
There's a chance that the rest of it's coming from the other parts of China. But no, I haven't heard a push for that kind of thing. Although, in a month, I'm supposed to go to Geneva if the coronavirus doesn't upset that plan, to the Ozone Research Managers meeting. And so they are another body that informs the parties of the protocol to plan and understand how the observational network, or how our observational and modeling network capabilities need to be adjusted to put us in a better place to answer these questions. And one of the biggest issues on the table at that meeting will be, how can we improve the observational network so that we don't have these gaps, so that we can understand global changes better. Yeah.
Are there certain reasons why you think that this protocol was more successful than some of the more recent attempts? Like, it seems like if you were to, when you say, oh, everyone votes on these unanimously and it all gets done, I'm pretty surprised, because it seems like usually that's not the case with the international community working on things like this. Do you think there were things about this that made it more likely to be this successful?
Yeah, well, relative to greenhouse gases, I think there's a number of things that come to mind. And one is that even though halocarbons, these ozone-depleting substances, were central to many different aspects of society and the benefits, refrigeration, air conditioning, solvents, all that kind of stuff. There were many different aspects. They weren't central to most countries' economy. That's one thing. Another thing is that the threat was real, and there was a canary in the coal mine that it was dying over Antarctica. I mean, there was this huge red flag that substantial and in certain regions of the stratosphere, complete destruction of ozone was happening in that certain layer where we expected the most. If that were to happen throughout the world, we'd be in deep trouble. The fear that I mentioned in the scientists, I think, was noted by everyone, policymakers too. We need to do something. They all were willing to come on board. Sure, after a lot of pushing and pulling, negotiating, and other things like that, but ultimately, it's clear that the parties are dedicated towards finding a solution and making it work. And it seems to me that's the key. And as soon as everybody's on board that way for any other issue, then maybe it'll go easier. Yeah.
But wasn't it also true that at that time industry really had substitutions ready to go on a commercial scale? And it seems to me that is an important piece that makes the climate change issue much more difficult than the ozone issue.
Yeah, I agree completely. Initially industry wasn't on board, maybe until they realized that they have substitutes, and then they came on board. But that was a difficult process originally. I mean, Sherry Rowland took a lot of abuse years ago. Then they came on board, but there were still many, even the methyl bromide community still pushes back on these controls. And so in order for success, agreed, you need to have them on board too. And if the issue is substantial enough, that they care enough about it, and then they will find a way. Yeah.
You said that on one of your slides that the scientists gave policy relevant but policy neutral advice.
Yeah.
How important do you think that is? If you all come in and said, HFCs are evidence we need to abandon capitalism. If you think it would have gone well.
HFCs are what?
If you had gone and said HFCs are the reason we need to abandon capitalism, would it have gone badly? That's a bit of a loaded question, obviously.
Oh my gosh. Is that important? It's absolutely critical. You know, the last thing policymakers want is somebody with an agenda supposedly coming to them with objective scientific results. If they can't rely on the scientists being objective, all's lost. Their information is biased. And so it is critical. The amount of time that we write these quadrennial reports, and it's a big body of scientists who work for a week on just an executive summary. And we work on every word, every phrase, and a big part of that is not providing policy recommendations. We own only part of the equation, part of the landscape with respect to a policymaker making decisions, and that's the science part. How you implement some goal that you might think is a goal you want to attain involves so much more information, so much more consideration that scientists aren't part of. You know, so I can say, if you want to avoid a temperature increase of 2 degrees C in the next 100 years, then something the carbon emissions have to be reduced from what they are. You know, if then, you give them the chance. You don't tell them, shoot, you got to solve this problem by cutting fossil fuels. You know, you can reduce carbon emissions without cutting fossil fuels. Maybe. Could you do it? I mean, you can. The question is, do you want to go through that effort? You know, that's for them to decide, because that landscape is so much more complex and difficult. We let the more intelligent folks answer those questions and deal with those issues. Yeah.
So just when you mentioned climate change, is the stratosphere cooling because of climate, and is that affecting the chemistry at all?
Yeah, there is some evidence that as the stratosphere cools, the ozone depleting reactions in the upper stratosphere slow down. And so we see some initial hints, I mentioned that, of ozone layer recovery. And it turns out that we think about half of it's due to the fact that the ozone depleting substance concentrations are reduced there. And the other half of it is because the temperature there has changed owing to greenhouse gases. And they're acting as a blanket down below so that less heat makes it up into the stratosphere.
Huh.
All right.
Great.
Thank you so much.
Thanks for coming.